So good evening, everyone. Thank you very much for joining. We are gonna start another talk in our Reasoning for Complex Data laboratory. We are honored today to receive Professor Nathan Jacobs to give this talk. Nathan will talk about mapping the visual world using webcams, cell phones, and satellites. Nathan earned his BSc in computer science at the University of Missouri and PhD in computer science at the University of Washington University in St. Louis. Since then, he has been a professor of computer science and director of the Multimodal Vision Research Lab at the University of Kentucky, which is the university where Rafael Padilha stayed for the last year visiting. Nathan's research area basically is computer vision, and his specialty is developing learning-based algorithms and systems for processing large-scale image collections. His current focus is on developing techniques for understanding the visual world from geotagged imagery, including images from social networks, publicly available webcams, and satellites. So, Nathan, thank you very much for accepting my invitation to give us this talk. I just gave you the co-host capability, so you can go ahead and share your screen. Thank you very much. I think you are on mute.
Okay, can you see the screen now?
We see the presentation.
All right, I'll share the other screen. All right. Okay.
Yeah, please go ahead.
Good. Okay, fantastic. Okay, yeah, so the talk today, and thank you for the introduction and the welcome. I'm excited to get a chance to give this talk. And it's going to be kind of a wide-ranging talk. I'm happy to get interruptions whenever as we go along. I think that'll make it more fun. And yeah, so the title is Mapping the World Using Webcams, Cell Phones, and Satellites. But I thought I would start from a long time ago in relative terms with this planoptic function. Right, so this is, this is from, probably before many of the people in the audience were born, but the idea is that you can represent the visual world as a function, and it's a function of the angle that you're looking, the wavelength of light that you're paying attention to, when the picture is taken, and the geographic, or in the location, right? And so this function represents the visual world in some sense. And a lot of my work, I sort of trace back to thinking about this function, and generally what I like to do is think about ways to extend this function, right? And so we can think about that extending that in various ways. So we can think about adding additional things that we're modeling. So we can start modeling semantics, right? So we can model the intensity of every pixel. We can also model, whether that particular direction in the world is looking at the ground or looking at a vehicle. And so this now becomes a more generalized planoptic function that can represent all sorts of things. And then if we take this, if we just take this function and we reparameterize it a little bit, replacing x, y, and z, which we often think about as being defined in some local coordinate frame, and instead redefine that in terms of geographic coordinates, in terms of latitude, longitude, and the altitude, we start having this sort of more generalized planoptic function that represents the Earth. And for me and a lot of my work, I've been interested in thinking about this broad function that can represent all sorts of different things and what we can do with that. And in the end, what we get are maps, right? These are maps that represent the visual world in some way. And we can think about, maps sort of like satellite imagery. We can think about maps as representing some sort of semantics. And so where did I was sort of thinking about this talk and trying to, frame it. And so I thought I would start with, where I started in all of this. And so as a grad student, I was working on the problems of visual surveillance And we started thinking about this, people started posting outdoor webcams all over the place, and they were allowing us to stream images from anywhere in the world at all hours of the day. And we started building this collection of imagery from webcams. And that continued through about 2017, but ended up with quite a few images from all around the world, and we've been able to do lots of interesting things with this. But during my grad school days, essentially one of the key things that we were looking at is, how do we factorize these sets of images that we get from an individual webcam? And so you can think of a webcam as it's just a sequence of images that you get from that. Each of those has a timestamp, and generally those cameras are well aligned. And so, every pixel is looking at the same point in the world over and over and over again. And so some really simple models work to extract information from that. So one thing that you might do is run principal component analysis on this. And the way that looks is that you take your stack of images, and you basically turn those all into vectors. And then you have a matrix of all of these pixels, and then you approximate that with some low dimensional pair of matrices. So that you have a set of basis vectors that represent the layout of the scene, and those might look like this. And then what's cool about this is that you have a set of time series that go along with these, right? Because every image has a timestamp. And so this is a way to extract time series from outdoor imagery. And what's interesting then is if you look at these time series that you get by just running PCA, you get coefficients that are representative of various visual phenomenon. And so that first coefficient tends to be whether it's day or night. The second in this case happens to be whether the scene is foggy or sort of overcast at that time. And so that becomes then this signal that represents how the world appears and how that changes over time in a sort of a more general way than just thinking about individual pixel trajectories. And one of the things that we started doing was sort of thinking about how can we use this? This is kind of an interesting thing that just happens. And so one of the things that we did was to apply this to localization. So the basic idea there is that if we think about a year as the different hours of the day and the different months or the days of the year, we have these coefficients up here that represent a particular point in that trajectory, in that space. If we start pushing those coefficients and displaying them like this in terms of hour of the day and day of the year, we get images that look like this, where the red parts are places where the camera was down or the server collecting the data was down. It turns out that you can do a really good job of localizing one of these cameras by just looking at these boundaries between dark and light. And so essentially, you can estimate your latitude and your longitude based on the shift of this and based on the shape of that trajectory. And so that's kind of a cool thing that, you start discovering that, discovering is probably a bit of a stretch, but, you start realizing that this imagery is telling you things that relate to geographic location, that relate to time. And so we also then, we're thinking about what are the other things that we can make this relate to instead of just, dawn and dusk. And so we started looking at how we could use satellite imagery. And so the idea here is that you've got a trajectory of PCA coefficients from a camera. And then you've got a satellite image, and you've got a sequence of these satellite images collected over time. And if you've got the satellite images at the same time that you have the webcam images, you can then essentially search in the satellite imagery for pixels. Hold on a second. You can search in the satellite imagery for pixels that have the same coefficient trajectories or similar coefficient trajectories as the webcam imagery. So essentially what you can do is search over the satellite imagery to find pixels that have similar trajectories, and then that becomes a way to get a strong cue to localization. So that's really, where we started in thinking about this relationship with, appearance and time and location and satellite images and ground level images. And with that work, we sort of built that out in different directions, able to do scene geometry estimation. So, very fine-grained localization is one way to think about that. Estimating the orientation of the camera, registering sets of time-lapse images, estimating weather conditions, doing environmental monitoring applications. And so this all sort of, I sort of intentionally picked this 2013 date because this is sort of the pre-deep learning era, using fairly simple methods. And so that's, just to put you in the mental frame of mind of, me when I was a grad student and a fresh faculty member, sort of looking at the world. And so what I want to transition into now is, sort of where we've gone with this. And so revisiting this sort of general idea of this planoptic function and representing that in terms of latitude, longitude, and altitude parameterizations. What we'd like to be able to do is represent any sort of useful visual phenomenon that would be useful to map. And I'll leave that to you to imagine visual phenomenon that you might think would be worthwhile to map. But we have the basic gist of this is that what we're trying to do is to use whatever source of imagery that we have to try to build this planoptic function. And so we've got webcams. Those are really interesting because they're temporally dense. We're collecting images maybe every 15 minutes or every 30 minutes, potentially more frequently than that, but they're spatially fairly sparse. Social media provides a lot of images, but those are still fairly spatially sparse and also temporally sparse, and they're very biased based on who's collecting the imagery. There tend to be lots of pictures of, people taking pictures of the food they're eating or of themselves and their friends. Something like Google Street View is interesting because it has very wide geographic coverage, but it's fairly limited in that it's mostly along roads. But in the end, the work that we're doing, the idea is to let's find ways to combine all of these different sources of imagery to do useful things in terms of representing this planoptic function. And the key things that we end up using are, sort of cross-modal distillation. That should be cross-modal, not model. And we'll talk more about that. And in general, sort of contrastive learning sorts of approaches. So we're going to divide this talk, sort of the more technical aspects of the talk, into a couple of areas. One is on mapping semantics, and we'll talk about 3 sort of detailed areas there, and then more broadly, some more recent work on dynamic visual attributes and mapping those. So just, I think probably everybody in the audience is somewhat comfortable with this concept, but it's not, everybody doesn't know this. So, but image understanding for ground level images finally works, right? It's not perfect, but it's, if we look at what it was 10 years ago, it's dramatically better. And so a lot of what I'm going to be showing relies on this. It relies on the fact that there's been countless numbers of GPU years, probably GPU centuries put into training models that are able to understand ground level images and huge data sets that enable us to train these models. What that means is we have these beautiful little compact models that represent the ability to extract information from images, right? And these images, if they look roughly like the images they were trained on, will work reasonably well. And so we'll sort of build out from that to try to extend these semantics that we can extract from these images to a more broader sort of the planoptic function viewpoint. So one of the things that we'll look at is this cross-modal distillation approach, and we'll talk about 3 different ways that we've done that. And so the starting point of this is to imagine that you've got a set of ground level images like these right here, and you've got a set of target labels that for some reason you care about. And then somehow you're going to train a model to be able to extract these on new images that you receive. That's a pretty standardized process. And with a fairly small amount of labels at this point, you can do that as long as the labels are somewhat similar to available pre-trained models. So now we have a set of labels that we can extract from our ground level images. And so then what we can do is we can take a particular geographic location, we can get a ground level image of that location. And so this is going across the top. We can extract those labels from that ground level image. And then for that geographic location, we can do the same. We can get a satellite image of that location, for instance. You could imagine that being another kind of image. But these are images of the same geographic location, just from different perspectives. And the issue here is that we don't know how to extract the semantics so easily from the satellite image, but we can easily extract them from the ground level image. And then what we can do is we can train a neural network here to extract information that matches with the information that we're getting from the ground level imagery. And so we can think of these labels that we get out from the ground level image as a set of weak labels. They're not as good necessarily as human annotated ground truth, but they represent some form of truth, and allows us to train a model that can extract the same semantics from the satellite image. And then what that allows us to do would be to fuse information, right? So we might, given a query location, get a large number of ground level images, get a satellite image, somehow extract all of this information and fuse that to build a map, right? And that map, in this case, we can think about that as our planoptic function, sort of generalized function that represents some semantic property for a given location. And we have some work that's sort of focused on this fusion aspect of this, and I'm not really going to talk about that in this talk. Mostly focused on the distillation part. So how can we take information from the ground level image domain and learn to extract that from the satellite image domain. And the reason we want to focus on that is because, as we saw, the ground level image domain, either with street view images or the webcam images or social media data, those are all sparse in some way. And the satellite imagery is wonderful in that it's dense, broad spatial coverage with providers like Planet giving you images every day. And so being able to interpret that sort of imagery automatically in a way that is related to things that we might care about in the ground level imagery is a really powerful building block. So we built a data set we call CVUSA. It's a set of pairs of 1.5 million ground level images collected from Flickr and Google Street View. And with each of those images, we have satellite imagery at 3 different spatial scales. And so we've used this data set for a lot of evaluation and experimentation in this space. But one of the first things that we did was to run an existing scene classification network. This is the Places network that tells you whether a particular ground level image contains pasture, cornfield, or it's a parking lot. And then if you just map that, if you just make a scatter plot color-coded by the semantic label, you get a map like this of the United States. And so what you should see here are some patterns, right? So we sort of see places out here in the West where there aren't a lot of images because there's a lot of open space. We see dark blue areas up here that seem to, I think those probably relate to corn or some sort of agricultural use for that land, and so on. So these are sort of patterns that, if you know the United States well, should step out to you. But you can still see that there are holes. And as dense as this looks over here, that's only dense because we're using very large circles. So there's lots of holes in this. So this is where being able to apply these networks to train satellite image understanding networks is really helpful. So where we follow this process, we take some ground level images, we extract the semantic labels, we train a network to predict those semantic labels from the satellite imagery. And what we get is a network that we can run anywhere in the world that will tell us things like, this is probably a field, this is probably a train station, and it actually works surprisingly well. And so I don't have any great maps showing that, but what we end up doing is sort of thinking about how this relates to localization problems. Because that's a really nice way to evaluate some of these approaches. And in general, we tend to think of there being some sort of duality between tasks like the sort of planoptic function mapping problem and the localization problem. So if you can have a very accurate planoptic function, it makes localization really easy. And if you know how to do localization, then maybe you can do this planoptic function mapping really well. So we can construct these sort of ad hoc maps, which I think is kind of an interesting application. So we can take, for example, this ground level image here, extract the description of that image. And this is going to be just a vector that describes that image. And then we can essentially run our satellite image understanding network across this satellite image and compare the satellite image location with the vector that we got from the ground level image. And that becomes a way to, essentially search for places. You can think of this as like a retrieval setting where we say, here's the query image. I'm going to try to retrieve locations that are similar to this. So that allows us to construct maps that look like this. And so what you'll see here at the top is a query image. We have a satellite image that we've run our satellite image understanding network across convolutionally. And then at the bottom is a heat map. Essentially what this shows is the red areas are places where the feature vector from the query image and that location were very close, and the blue areas are places where that feature vector was very far. And so what it does is it allows you to sort of, visualize, places where an image like this might have been captured, which is essentially a form of localization, sort of a weak form of localization. And you can also do this, you see nice patterns at broad spatial scales. So, if you know the desert southwest of the United States, this is essentially highlighting places where, this image was probably classified as a butte or something like that. So this is some of our work on this problem of cross-modal distillation between scene categories from ground level images and satellite imagery. And this is really where we started working on this problem of, localization, very broadly. And so I thought I would just throw in a couple of, I'm not going to talk a whole lot about these two things, but we've also done some work on global scale localization using reference data sets that are ground level images. So what I showed before were reference sets that are satellite images, and you can do localization. But this is a visualization of what that might look like if you're using ground level images. So given a query image, extract a feature vector, find nearby locations, nearby images in the database, plot those, and then use a density estimate. And so maybe this looks like, it's either in Europe or the United States in this case. We've also more recently been exploring more localized pose estimation. So for example, we've got some work that's under review, looking at simultaneously doing depth estimation and scene coordinate estimation. So the distinction being both of these are geometric problems where we're estimating how far away a point in the scene is. And here we're estimating a particular point in the scene, exactly where is that in some scene or global coordinate frame. So it turns out that there's a nice way that you can essentially, in a fully end-to-end differentiable way, combine these by essentially thinking about these two as separate point clouds that you then do a rigid alignment to. And so you can optimize for scene depth estimation and scene coordinate estimation simultaneously with getting pose estimation. But that's sort of, these are both sort of focusing more on the discriminative side of this problem of mapping. And so I want to focus more on the sort of the mapping side of it, but I thought I would share those. So we talked about scene classification and doing this cross-modal distillation for the scene classification task. And so now what we're going to do is look at the same thing, but for object detection. Right? It's a very similar process. Essentially we take pairs of images. We've got satellite images, we've got ground level images. We run an object detector on the ground level images. And for each of those, we basically build an object histogram. So we know how many of a given type of object is in that ground level image, which tells us that at a given place and time, that's what objects we would expect, that were visible in the scene. So in some way that becomes a label that describes a location in this satellite image. So we have a data set, we essentially ran some off-the-shelf object detector with 91 different object classes, using, once again, the CVUSA data set, a subset of that. If we just take the CVUSA data set and we look at the objects that we detect, and we try to make a map directly from that imagery, just from the ground level imagery, we get maps that look like this. And so I think the most interesting one is this train map on the bottom left. And so if you know the United States, you'll recognize that there's Chicago is right here. And essentially what this shows, wherever it's darker green, is a place where if you were to take a ground level image at that location, then it's likely to contain a train, right? So it's more likely to contain a train wherever it's darker green. And so this is essentially laying out the train infrastructure for the United States very roughly, but you can sort of see the evidence of that. Now, it's nice that that shows up, but it's also very low resolution and essentially useless for any practical purpose. And so this is where the cross-modal distillation becomes really helpful. So this is the basic process. We run an object detector on some image that we know its location. We have a satellite image of that location. We build an object histogram from the detected objects, and essentially we just take some off-the-shelf neural network and we optimize it, to predict a distribution over the object histograms. So if it's likely that a picture of that location would have a boat in it, then it should predict a high value for that. So now we have a network that we can run anywhere that tells us how many of a given type of object we expect to see in that location. And so with that, we can make much finer resolution maps. And so here's an example showing the San Francisco Bay Area, which highlights things like where the road network is in the San Francisco Bay Area. Right, so if we're expected to see a truck in a picture, you can see these, truck routes where trucks tend to drive are highlighted fairly clearly. Boats are highlighted fairly clearly here, so they're typically in the water, and so on. In addition, we can look at, sort of in some sense, look at what the network has learned. And so what these are, we basically looked over the entire San Francisco Bay Area for the satellite image chip that has the highest expected number of a given object category. So this is the satellite image chip in the Bay Area that if we were to take a ground level picture at that location, we'd see the most boats. And so it's not perhaps that surprising. And this is the airplane one, and this is the surfboard one. And so it's actually pretty cool that these, we've essentially discovered this, trained this network to do this semantic extraction without any manually annotated training data that we had to construct. We were using off-the-shelf network for understanding the ground level images for this training process. And then we've also looked at the semantic segmentation task in a, once again, it's a similar idea with just a rich source of supervision in that we take a ground level image, we run a semantic segmentation network. In this case, this is some older work, and so we used an older neural network architecture for that, and we get a low resolution semantic segmentation, which we could make better today if we replaced that with a better segmentation architecture. But the idea is that what we like to be able to do is to somehow transfer the semantics from this to the satellite image so that we can label every individual pixel in the satellite image, even though our training data, consists exclusively of the information that's inside of this neural network for understanding the ground level imagery. So the basic idea is we have a satellite image, we have some extraction that gives us pixel level labels, we apply a spatial transformation to make this, basically look like it's from the ground level image perspective, and then essentially we can just train this with cross entropy. And so this left side over here is a fixed network that we just downloaded. And so what we're training here is this extraction process, and actually we're training this spatial transformation process because we don't necessarily know exactly how to transform the geometry here, because the world, if the world was flat, it would be easy, but because the geometry is unknown, we have to do a little bit more work to do this transformation. So this is what the more detailed view of the architecture is. So this part up here, let's not worry too much about this. This is just some semantic segmentation architecture. And if you were to redo this today, you would probably replace that with something else. So this is just some semantic segmentation architecture. We get an aerial image segmentation map. The important piece here is that we also have this transformation. And there's lots of different ways to try to represent this transformation. The way that we found that worked really well was actually representing this as a dense matrix multiplication. So in general, if you take an image and you vectorize it, and then you have another image that you're trying to transform that into, and you vectorize that, a matrix multiply on those vectorized images can represent any operation that you want. It can flip things upside down, it can rotate, it can scale and stretch. And so essentially what this is a matrix that represents, from a value in this pixel in the source image, where does it go in the target image? And then we actually generate this, this is actually the output. Each of these elements in here is the output of some separate neural network, right? So essentially we have a parameterization that says, extract some information from the satellite image. This is going to represent scene geometry in some way. Define which pair of pixels we're trying to map between. So is this the top left image going to the bottom right of the other image? And then we have a multi-layer perceptron that we basically learn to map that into these values here that represent the spatial transformation. And so that dense transformation actually, made this fairly easy to optimize. But what's cool about this is, in the end, you've taken the semantics from this ground level image and you've transferred that into the aerial image. And so what that does is it gives us a network that can now do semantic segmentation of the satellite imagery without ever using any semantic segmentation labels for satellite images, which is, I think, a fairly cool thing to be able to do. And it's not great, you'd probably want to fine tune this with some real data in this domain, but you might be able to use this to significantly reduce the amount of manually annotated training data you have to collect. So we showed how to use this for ground level image orientation estimation. So imagine you're in an autonomous driving scenario or something like this. You can, if you know your location, but for some reason your orientation estimation isn't working well, you could potentially use something like this, where you take the ground level image, you extract the semantic segmentation. This is the semantic segmentation that you get from the satellite image. And then essentially you just compare the extracted semantic segmentation from the image and the segmentation you get that you predict from the satellite imagery. And then we showed how we can essentially score these various rotations to find which ones are most likely. We also showed how we can, that we can synthesize pixel values as well. Right, so given a satellite image, and this is the corresponding ground level image of that location. So the top image here is the real ground level image, and these are our synthesized ground level images. So essentially, we predict the semantic segmentation and then essentially put an image to image GAN on top of that to predict these pixels intensities. And so that's kind of an interesting application where you can synthesize ground level image appearance from the satellite view, which might be useful for various applications. And there's been some work, this isn't the state of the art on this task anymore. There's been several papers that extend this basic pipeline, as GAN architectures have improved. And so recently what we've been focusing on, is this image synthesis problem sort of came out of our interest in, synthesizing ground level images from satellite images that we just showed, but trying to find various ways to improve that. And so this was a recent BMVC paper that we had. And the basic idea here is that you want to go from an input image and you want to output an image. And generally what you're given as training set is a pair of images that are close. You know, they might be a few meters away from each other. And then there's some known translation. You know, did the camera move forward or backwards or left or right? And so there've been a variety of approaches to this. And so we've, you know, built a hybrid approach that allows you to combine a couple of these different approaches. So with the first approach here on the bottom is this flow-based synthesis. So the idea is that you take your input image, and your camera motion, and you predict a displacement field. So this is a, you know, essentially a set of vectors that represent how pixel intensities in the image would move based on that particular motion. And then essentially you can just apply a linear interpolation to get your output image. That works quite well. You get nice sharp outputs, but there are artifacts, and it's not able to synthesize missing values either. And so the top part is essentially doing a more direct synthesis, where in this case, the clever idea was to integrate the flow field here at the bottleneck to allow us to know a little bit about the spatial transformation that we need to apply. And then there's a fusion process at the end. And so this is a different way of looking at this problem of synthesis, less dramatic appearance change than going from a satellite to a ground level image. But we're sort of heading in this direction of trying to be able to use, arbitrary view and another arbitrary view of a scene and being able to transfer between those to be able to synthesize one view from another. One of the lingering challenges, and this is work that we've been, we were busy with this fall, was dealing with the fact that, often when you get a pair of ground level images from something like Google Street View, they were captured at very different times. So you might have one that was captured in the winter and one that was captured in the summer, and they look different. So we've been trying to address that problem by, the problem that causes is that when you go back to this process here, essentially there's an error that you have to place here between the synthesized image and the target image. And you'd like that to be a squared error or some simple term like that. Well, that doesn't work well if it's captured at dramatically different times. So we've been looking at ways to replace that with approaches that, for example, here we have a target image and a source image that look quite different. And the unique idea here is to take the target image and essentially get a style encoding of that, and then use that as input to our decoder to generate the output from this source image. And what's interesting about this is that as sort of a byproduct of doing that, we're able to learn to synthesize images in different conditions. So here's our result for a ground level image as an input, and then these are the reference images. These are essentially the style images that we're trying to match. So you can see the synthesized images from our approach here, and then this is a prior approach, a recent approach, and the images that are synthesized using that. So some improvements, but to some extent I think that's an important result, but I think to me, what's interesting about it is it allows us to train on pairs of images that are very, very different. Okay, so I know I'm kind of covering lots of different areas here, but that's the end of this sort of mapping semantics component. And now what I'll do is focus on this sort of mapping of dynamic attributes. So, everything I've talked about before, we've been thinking about static attributes, and those are easier to think about because if you have to think about time, you have a lot of changes that are incurred, and so you have to think about how do you represent changes with respect to time. And so let me kind of go quickly over this. I want to leave 10 minutes or so for questions and discussion. So some of our first work on this problem actually comes back to our very early work with doing PCA for image factorizations. But the gist of this is we can think of training a neural network that takes in an image. And so we just look at the top here, takes in the image and time. And if we follow this pathway across the top, we predict a distribution over locations. And at the same time, we can take the image and the location and predict a distribution over times. And so we can actually train this whole network end to end. And what's interesting about this is it helps us extract features from the ground level images that are related to location and time. And then it's essentially building some sort of map of the visual world because it allows us to take these locations and predict time. And so just a little bit of the evaluation, sort of it shows that if you look at, for example, this green line here, so this is the ratio of example images that were correctly localized within, say, 1,000 kilometers here. So if we include time, we get, over 40% of them correctly localized. If we don't, we only get, say around 30% correctly localized. So one of the things that, comes out is, if you know when an image was taken, it really helps you estimate where that picture was taken. We also discover, interpretable attributes. So these are, if we just look at the features that we extract from the imagery, and then we plot those with respect to time for a given scene, we see these trends. And so this first one actually is just, is it day or is it night? And the second one ends up being whether the scene is foggy or not. And so without any, explicit annotation to say, I want to learn to recognize foggy images or day versus night, we've sort of discovered that just by trying to estimate when and where a picture was taken, which I think is an interesting outcome. So we've also extended this work to thinking about mapping traffic. And so this is a data set that we worked with. This is a CVPR paper this past year of traffic speeds from the Uber movement data set. And the basic idea is sort of shown in this picture, in that we will take a satellite image, the location and time that the image that we're interested in, and then predict several different things. So where are the roads in the satellite image? What orientation will vehicles be traveling along that road? And at what speed will they travel? And so, we have this data set here. It's got a lot of missing values in it. So there are places where the Uber vehicles didn't drive. And so what we're able to do is to essentially fill in the missing values. So we're training a network to, estimate traffic speeds on roads where no vehicles ever, no Uber data was ever collected. So I think there's lots of potential applications here for, deploying autonomous vehicles, especially going into new areas where you might not have data about, what's happening as clearly. And we have results sort of showing that, adding location and time helps, and it helps in different ways depending on the task that we're asking it to perform, but I won't go into that. It does allow us to make maps that represent sort of travel time. So we can see things like we can travel much more quickly from this location in Manhattan at 4 a.m. than we can at 8 a.m. Because the traffic has become more congested and the traffic speeds have gone down. We've also been working on mapping visual attributes. And this is very similar to that first thing that I talked about, mapping the, discovering attributes. But here we're explicitly training to predict these attributes. So here we have a satellite image. We have the time that a ground level image was captured. We have the location that it was captured. We've got the image over here. We extract some attributes from that. And so this is this cross-modal distillation idea once again. And the idea is that with the satellite image, location information, and the time, we train this entire network over here to predict these things that we're extracting from these ground level images. And in the end, what that gives us is a way to map whatever visual attributes we have over here very densely in time and space. And so here are some of the maps that we constructed from this using these transient attributes that are defined in this transient attribute data set. And so for attribute lush, which is essentially how green and full of vegetation a particular area is. We can see that the United States, blue represents, not very lush, and then, by July, it's very bright, it's very green, and so wherever it's yellow represents that. And then, this is essentially showing that the Pacific Northwest of the United States is fairly gloomy in January. And if you've been to Seattle in January, you know that it's likely raining and maybe foggy. And so what's interesting is that we sort of discovered the ability to map these visual attributes without any new training data that we've collected. This is just using distillation between the ground level images and the satellite images. And so this is the mapping side of things. But remember, there's always sort of this like duality between, if we can do mapping, we can do various applications. And so one of the applications that we showed in that work is in content-driven metadata verification. So the idea here is that somebody has given you a ground level image and they say it's captured at a particular time, right? And you want to verify whether that time that they say is correct. And so what we can do is, if, assuming that we know the location of this image was taken, we can get a satellite image of that location. And then what we can do is essentially match the the visual attributes that we extract from this image with the attributes that we can extract from this map that we've trained, right? And so recall that, we have a neural network that is constructing these maps. So we can sample this neural network on the left wherever and whenever we want. And so what we can do is sample at all the different times of day, all the different months of the year, and compare those. And wherever it's green is saying the visual attributes that we would expect at this location match with what's in the image that we've received, that we have up here. And at the X in this case is the actual image location in sort of time. Similarly over here at the right. And so, just to brag a little bit about Rafael, who was in my lab this past year, some of the work that he was doing was extending this, with the idea that what we were doing before was not trained in a discriminative way, right? It was trained just to make the maps. And then we said, oh, now that we have the maps, we can do this other task. And so he was looking at ways to make this a discriminative task. And so the idea here is, given a ground level image, the time and location, and a satellite image, if you let's not pay attention, let's not worry about the bottom ones here, but if we just focus on this up here, essentially this is saying it's a binary task. Are these consistent or not? Right. So if we train for that, it actually works out quite a bit better than what I just showed. And so here are the heat maps for this. Similar idea, we've got pairs of, we've got a ground level image. We want to know when this picture was taken. This is the old method. And so you can see that it's a very broad distribution. It's, it's yellow almost everywhere. Whereas with the discriminatively trained approach that Rafael is working on, we get a much finer grained, more precise estimate. And this not only shows up in the the qualitative results, but it shows up in the quantitative results as well. And so it's another example of, where you can use this cross-modal, this training process that's combining satellite image and ground level images to, essentially be able to do a verification process across that planoptic function. Okay, so I'm pretty close to where I was trying to hit time-wise. So just in sort of summarizing, I know I covered quite a few different areas. Been interested in thinking about this planoptic function and generalizing it to include semantics, to include objects, and to be in actual real-world geographic coordinates. We showed a few different examples of mapping various visual attributes. And then showed how the sort of mapping task connects to various traditional vision tasks, from the metadata verification example to the localization and pose estimation examples. And with that, I'd like to thank, this work wouldn't have been possible without, hardworking students that put in lots of hours, building data sets and training models and evaluating them. So just want to thank all the people that helped with that. And with that, I will be happy to take questions.
Thanks a lot, Nathan. Very nice and interesting work. And the more I see these new applications, I remember the difficulties that we had like 10 years ago, trying to solve some of these problems using like fine transformations and the need to localize discriminative points. And for many problems here, it was not even possible because the transformation is not simple to calculate and perhaps too complicated to rely on points. And so basically SIFT is dead and the related things to SIFT are not that used anymore for this kind of problems at least. And I can see also that we are relying on deep learning a lot. And I would like to start asking you, what do you think about this? Being like a core vision researcher, we see that some vision researchers, they don't like this reliance on deep learning techniques, and they still struggle trying to solve this geometrically and mathematically. But more and more I see that deep learning can be of help. And how do you feel about this?
Yeah, I mean, I think there was certainly, especially, when deep learning first started, you saw a lot of people walking around conferences, sort of hanging their heads down and being, disappointed and sad because they didn't like the character of the new work. But I think that there are clearly engineering challenges that are very different when you're working on deep learning sorts of approaches. There's something beautiful about being able to sit down in MATLAB with a few lines of code and hash out your geometric details, and it all just works nicely. And when it's done, it's perfect, right? And so I think there's a really big, just a mental mismatch between this sort of more theory-driven traditional computer vision and the more data-driven new computer vision that I don't think that, I think it's good to have people on both sides, and you're starting to see more of those traditional geometric ideas coming back into it. And so, recent work on, learning to do matching through epipolar transformations and things like that. So I think, as much as I think there was a lot of low-hanging fruit for about 5 years that allowed you to just sort of make improvements on the learning side. But I feel like at this point, a lot of the really low-hanging fruit has been consumed. And so you're seeing, larger models, larger data sets making big advances, but you're also seeing more traditional geometric vision ideas sort of starting to find their way back in different ways. As we, part of that is finding ways to make more things than we thought before differentiable, so that we can differentiate through more things than we could before. Anyway, yeah, no, it's an interesting thing, and it's been an interesting 10 years to be working in this field because it's changed quite a bit.
Yeah, it changes significantly. Thank you for your answer. Folks, if you have questions, as you know, please type them here and I'll go through them. While I receive these questions, I'll go through some that I got before. One other question that I have here, Nathan, is that for many of the problems that you mentioned here, you are relying on outdoor cameras. And most likely, when these cameras are static, the modeling is easier. So how do you deal with this data coming from cameras that are dynamic? So they keep moving during the day.
Yeah, so are you talking about webcams that are changing their direction, or are you talking about sort of autonomous vehicles?
Well, autonomous vehicles are more difficult. I was more into the first side.
Okay. Yeah, so okay, I mean, I think that because the autonomous vehicle case is probably easier because they're probably fairly well calibrated,
Mm.
and so you know that really well. So, but yeah, so for webcam data, that was actually a huge problem when I was a grad student because we tried to use PCA for everything, right? And PCA, you sort of expect that things are aligned,
Mhm.
right? That's why PCA tends to work well on faces because it's fairly easy to get the faces aligned, and you have nice frontal faces, and it just kind of does something reasonable. Um, but if you've got a camera that moves quite a bit, and especially if you're trying to do long-term analysis, so we were trying to do things like look at images across an entire year from a camera. So even beyond the problem of a camera that changes dramatically because it's got some schedule that it's running on, it starts to snow, and a little bit of snow gets on the camera and it slowly creeps down, right? So it was actually really hard to find cameras that were stable enough for a long enough period of time, um, which is actually one of the things that I was excited about with, let me go back to this work here. So with this work, part of the motivation with this was exactly the problem that you're talking about. Whereas instead of trying to take all of the images from one scene and do some sort of factorization of that, which means that it should all sort of be aligned, what this is saying is we're just going to take an image, and I don't actually care exactly what the image is. If the camera's moving around, you can actually think of that a little bit like data augmentation, right? And so essentially what we've got is natural data augmentation happening if we've got a webcam here. And so it doesn't actually matter. It's actually helpful in this particular case if the camera moves. So.
Thank you. I have another one here. Do you think it's possible to apply this kind of algorithms to images with cloud interference when using, for instance, images captured by satellites outside the atmosphere?
Sure. So, I mean, a lot of our work, if I'll pick one for example. So this work right here. Um, so, one of our implicit assumptions is that we've got good satellite imagery that's free of clouds. Um, and so what this is trying to do, essentially what we use with these are base map images. So these are, satellite images that are constructed from a collection of many satellite images in an attempt to make them cloud free. And for a lot of parts of the world that works. And there's certainly parts of the world where it's cloudy so much that it's really, really hard to make a clean base map. But that's one of the assumptions that we make, is that those are clear. I think if we were to look at the mapping the dynamic elements of the scene, so if we go back to where's this? So this example actually, so here the input is a base map image. So this is a cloud-free, it's probably, cloud-free image, but our representation of time is only the timestamp, right? So if we were to replace this satellite image with an actual image that was captured on that date, then that might actually be helpful for this model, right? Because it would tell us if there's snow on the ground or if it was foggy. It would tell us some of those other things. So I think that is a direction to go forward, is thinking about how to use more frequently collected images, because I think you still want to have a relatively cloud-free, clean image so that you can understand the geometry of the scene and sort of what's in that scene. But then you also want to have something that represents the transient aspects of it as well.
Okay. One other thing that I was thinking, this is a question of mine. Do you have any kind of balancing when you train these solutions? I was thinking specifically in the case of rural areas. Normally, when you want to learn something about them, you have two problems. The first is naturally they have less images, so they are
Yep.
typically less sampled. And the second is the structures that you might have there will be more difficult to recognize or to segment. So when you have like an image from a rural area, basically probably you have like one or two big chunks in the segmented image, while for one in downtown Manhattan, you're going to have like lots of classes activated. So
Sure.
how do you do for training with this imbalancing and also these more complex situations of rural areas?
Yeah, so no, that's a great question. Thinking about the biases in the data set, um, you know, you have to think about what you actually want to do with the network that you trained at the end, and that will influence all of those decisions. Um, but I mean, when we were creating this CVUSA data set initially, like one of the things that we did was to use sort of a stratified sampling approach. So essentially divide the US into bins, and then within each of those bins, try to get as many images as we could, up to a limit. And so I don't remember exactly what the numbers were, but maybe no more than 10,000 in any given bin. And so that way we didn't oversample New York City, for example. Um, and so you can do some things like that, but it still doesn't really fully address the problem. So, for example, Nevada is, it's a beautiful state, but there are a lot of places that nobody ever goes because it's so far out in the middle of nowhere. And so we don't have ground level images of those locations. Um, but I guess one of the things that I like to think about is this image here, it's incredibly sparse because um, we're using ground level images. If we were to remake this using the satellite imagery, we could have satellite imagery everywhere. And so to some extent, like this approach where we train using the ground level images, but we can run inference on the satellite images, helps to mitigate some of these bias issues, because it has more complete coverage. Now there's still the issue during training, and then you have to come up with different strategies to balance that. And yeah, and so I mean, you run into this too if you think about, we got a lot of this imagery from Flickr, which has a lot of users from the US, right? And so when they would go to other places, they were going to tourist venues, tourist destinations in those places. So they weren't necessarily taking, very broad, they weren't randomly sampling the space of possible images to take. It was very limited. And so there's certainly that which we honestly have not tried to solve that problem in any way, but I do think that there's a problem there that would be worth sort of exploring. So
I have another one here from that's from Antonio. This one. Thanks for your great presentation. It seems that most of your work is done using CNN-based networks. Have you experimented with attention techniques over images? If so, do you think they are as useful to images as they are for texts, for instance?
sure. Yeah, so a lot of this work, we're the way I tend to think about attention on images is that it's often a way to get a few percent improvement on a given task. So we've done this in the medical imaging domain, which I didn't talk about any of that work, but we've explored attention, various self-attention mechanisms and channel-wise attention mechanisms in that domain. And it does, it can help. It can give you a few bits of performance improvement. But um, but yeah, I mean, I think what we've tried to do is focus a little bit more in our work on using mostly vanilla CNNs so that we don't have to, if we start including a little bit of attention in our CNN, then, the reviewers are going to ask for lots of different kinds of evaluation of those pieces. And so if we focus a little bit more on the high level, how to compose these architectures and use, well-established, easy to understand core components like ResNet 50 or something like this, that tends to help with that. And so it's not so much that I don't think attention is useful, it's just that we've avoided it because once you start introducing those hyperparameters into those little tiny pieces, then you've got a lot more experiments to run. So
Thanks a lot. I have one final question here, and this is like it's like an open question. Whenever I see works like this, we see many applications, but you have also possible downsides. So probably someone already talked to you and asked you about what happens in terms of privacy and surveillance and this kind of thing. So how do you feel about this? I know that the data that you have been exploring is public, so you can just go there and grab and do these calculations, which can offer you nice analytics about maps and allow you to learn things. But even in this case, probably someone will ask you what happens with privacy, and how do you feel about this in terms of your research?
Sure. So, for a lot of these tasks that we've worked on, we have, worked with fairly broad semantic categories. I mean, so if you look at this, in this slide, for example, right? So these are just very broad, is this a parking lot? Is this a cornfield? And so I tend to not be too worried about privacy issues when we're dealing with things at that coarse of a semantic granularity. We did some work with faces, with geotagged faces for a while. And with that work, there were certainly concerns, and we had to be really careful about, because we were doing similar work like this, but with human faces, right? And so that had, we had to be careful because there were geographic locations where maybe one person went and took 100 pictures of themselves, and then they posted that. And so then our model essentially learned that in this place in the world, you look exactly like, Joe, right? And so, but yeah, we're not doing any of that that work anymore. I think it's, there's a lot of, I guess what I tend to think more about are, what biases are creeping in because of the data that we're training on, right? And there are parts of the city where there's no social media imagery that's uploaded because maybe it's a lower income area, and so then you don't have a visual representation of that part of the world, or it's much lower represented. And so, yeah, I mean, I think a lot of this work has been a little bit more speculative and not directly tied into what somebody has an application for. And so I honestly haven't spent a lot of time sort of with that connection to a real application, because I think that that's at that interface is where things can go wrong. Like if somebody tries to start using this model that we've built to make policy decisions, right, then we have to go back from the very beginning and think about how we collected the data and how it's being used. So, I mean, I think, what I've seen is that, the connection that I've made is sort of, this is sort of helped me see what's interesting in the, remote sensing world. And so I've been looking for applications, sort of environmental monitoring sorts of applications that are connected there. So that's where I've been trying to sort of make that entry point. And so then, to be able to say things about the natural world, because all these ground level images give us really great, understanding of the natural world. And so that's the direction that I would like to take this, when we think about applications. And so I think, there are still certainly, economic and conservation related questions there that become sticky and messy. But I think maybe less on the privacy side as a concern.
Excellent. Nathan, thank you very much once again for your time. It was a really great talk, and the discussion's also very good. So thank you, everybody that joined us today. Thank you also for joining, and stay safe. Nathan, thank you very much.
Okay. Yeah, thanks so much for the invite. So hopefully we can see each other at a conference someday soon.
I hope so. I do hope so. It's too much time at home.
Yeah. Okay.
Bye-bye.
All right. Bye.